Well, hello. So today we explore the topic of a type of series called a Taylor series, and this is the goal being to find a power series representation for literally any function we want. And you'll see it's kind of limited. We can't do any function, but we at least build up kind of a formula for it. Okay, so I am going to take just a couple minutes at the top here just to actually develop the formula because I want you to see where these wacky numbers, and figures come from. So we start off by just taking a generic function f of x and saying, okay, let's assume it does have a power series representation. And to keep it simple, we'll just say about x equals 0 because we saw from before that makes the representation a little simpler. So that's what it looks like. That's a power series. The c's are the coefficients. So it's going to be something plus something times x plus something times x squared plus something times x cubed. And you know that some of those coefficients could be 0, so they could not appear. But really the only thing we need here is a formula for the coefficients, because a power series is just that. It's just a polynomial with a bunch of powers of x. Okay, so we get a formula for the coefficients in a pretty clever way. And this is it. So here's a clever way. Imagine plugging 0 into both sides of this equation. F of 0 is, well, this term has an x, and this term has an x, and this term has an x, and every single term has an x except this. So if x equals 0, the only thing that survives that process is C0. So therefore, we just found a formula for C0. C0 is just f of 0. So I'm going to put, once we get a little formula for the coefficients, I'm going to put it in red so you can keep track of them. Okay, so to get the first coefficient, you just plug in f of 0. And what this is really saying is we need the function and its series to hit at the same point. And so if x is 0, we want the polynomial to have the same value as the function. Okay, and then this number would determine what that is. And then, so here's the clever part. We're going to take the derivative of both sides of this equation. So the derivative of this side is just f prime. Think about the derivative of this side. It's, okay, c1 plus 2c2 times x plus 3c3 times x squared plus 4c4 times x cubed plus 5c5 times x fourth. So we're just going to use the power rule on that side. Okay, so that's all that is. We don't know what c1, c2, c3, etc. are, but we certainly know how to take the derivative of a polynomial. Okay, now plug 0 into both sides of that equation. So f prime is 0. So in this scenario, we know what f is. Imagine f is e to the x or sine of x or something. It's a known function. So we can certainly know what f prime is, and we can certainly plug 0 into it. But look what happens when you plug 0 into this side of the equation. Well, this term, all these terms out here have an x in them, so they all go away. So f prime of 0 is just the only thing that survives that process, which is C1. Okay, so that's the first coefficient. So if you were just looking at it now, you might think, oh, is C5 just going to be the fifth derivative? Not quite. If it were, then we'd be done. It's not quite that simple, and you'll see that. You'll see. Okay, so this is just a repeated process. Differentiate again. So f double prime is going to be 2c2 plus 6c3 plus 6c3x plus 12c4x squared plus 20c5x cubed. Easier to write than to say. Now, repeat. F double prime of 0, which again, we could and will calculate, is, well, every single term out here, once again, has an x in it, so they all go by, and the only thing that's left over is 2c2. So f double prime of 0 is 2c2, which means c2 is f double prime over 2. F double prime of 0 over 2. Okay, so a formula is revealing itself, but we're going to do it a couple more times until we really know what the pattern is here. Okay, so the third derivative, right? Go ahead. Oh, I wanted to make a quick note of this notation. Notice, I don't know if you've seen this before. This is really the first use in calculus you've had for derivatives higher than the second. You never really messed with the third or fourth or fifth derivatives in Calc 1. This little 3 here looks like an exponent. but I think you get the idea that it's not. It means the third derivative. Basically, when we get up to like the fifth and sixth derivative, we don't want to be drawing 6 little apostrophe slashes, right? It would just get messy. So that's it. That's the notation for higher derivatives. We just put a little 3 here, which, you know, looks like it's f of x cubed, but it's not. And I think you can see from this context that it just means the third derivative, okay? If I wanted the 20th derivative, that's a lot better than writing 20 slashes. Okay, so we just differentiate it again. So we get 63 plus 24c4x plus 60c5x squared. You can see, again, the only thing that's going to matter, though, is this 6, because now f3 of 0 is just all these x's are going to be 0. So 6c3 is the only thing that survives, which means that c3 is f3 over 6. Okay, so these numbers are seeming like kind of random, but I think on the very next one you'll see what these numbers are. Okay, so one more. F4 is just going to be what? 24c4 plus 120c5x. And then we're kind of out of dots. And then plug 0 into both sides. F4 of 0 is going to be, well, this goes away. And you don't see anything out here, but you get the idea that all these terms out here have x's in them. So it's just F4 of 0 is going to be 24c4, which means that the formula for c4 is F4 of 0 over 24. Okay, so obviously the nth coefficient includes the nth derivative, right? But it also is being divided by something. So think about, I think you hopefully know what these numbers are. What is, you know, how do you get 24 from 4 and 6 from 3? I mean, hint, the next one's going to be 120. Okay, so pause the video and think about it. What are these numbers? It's like 1, 1, 2, 6, 24, 120, 720. Those numbers are all the numbers up to that number multiplied together. Think of how you got it. You got it by 2 times 3 times 4 times 5. What's that called? That's called a factorial. Okay, so there's your formula. You take the nth derivative, and this is just at 0, but at something else it would be exactly the same. You take the nth derivative, and you divide it by n factorial. You don't have to memorize that, but that's basically what gives us our formula for these series. So they're just power series representations for any function, but because, you know, somebody figured this out, I guess somebody named Taylor, they're called Taylor series. Okay, so the nth coefficient, so the 10th coefficient is just the 10th derivative at 0. So you would literally have to do the derivative 10 times and then divide it by 10 factorial, which is a gargantuan number. So don't worry about that. All right, so if a is not 0, it looks exactly the same. It just has an x minus a in it instead of just an x. So in general, there it is. That's the formula for your power series. So there's a lot going on there. So let's pick it apart. So this is our series representation for any function, right? If we want to calculate this power series for any function, we just need to basically do a bunch of derivatives. And what that does, again, it makes the function match up at 0, but it also makes all its derivatives match up at 0. So it gives it like the exact same shape as the function at the point that we want it to, right? We want to approximate other functions with polynomials. So it's the nth derivative of a, and again, if a were just 0, this would be a 0, and there just wouldn't be anything here. Divided by n factorial. 1, I guess, I don't know if I mentioned that in this class, but you should know this. 0 factorial is 1. Okay? If you don't believe me, I'd be happy to explain it, but I think you should probably just take my word for it. 0 factorial equals 1. It just kind of works out with the way we conceive of factorials in terms of probabilities. Okay? So look it up. So look, that way you're not dividing by 0 here. It's 1. So it's f. So the 0th derivative is just f, right? So it's just f over 1 times x minus a to the 0, which is nothing. So that's your first term, so on and so forth. And you'll see, we're going to obviously do concrete examples of this. So, right, so if you were to expand it all out, this is what you get. You get f of a plus f prime of a times x minus a, because these are both over 1, plus f double prime times x minus a squared over 2. So that's 2 factorial is 2, 3 factorial is 6, 4 factorial is 24. Next term would be f4 over x minus a, I'm sorry, f5 over x minus a to the 5th over 120, which is 5 factorial. Okay, so these factorial numbers kind of popped up in a pretty unexpected place, and they did popped up because of the power rule, because if you keep using the power rule over and over again, you're just going to keep multiplying by the next number up. So the general term for that is a Taylor series. In the case where x is just 0, so a Taylor series, I'm sorry, not x, but where a is 0, so a Taylor series centered around 0, for some reason just has its own name, and it's called a Maclaurin series. Okay, so that just, it makes it a little simpler to compute, but it just turns into that. So there's no x minus a in it. You're just doing derivatives and plugging in 0 for x. All right, so for whatever reason, that has its own name, named after, you know, some Scottish mathematician. So all that is to say, if I ask you to find a Maclaurin series, you know what I mean. You mean the Taylor series or just power series representation for our function about x equals 0, because it's just easier that way. So picture the graph of sine of x, and remember what I'm asking you for. I am asking for a polynomial that looks exactly like sine of x, at least near the origin, okay? And we'll get that. This one, some of these, you'll be surprised at how well they work and how nicely they approximate the function. Why would we need this? Well, there's reasons. Okay, so the process is kind of tedious almost. You just keep calculating derivatives, and then you have to find a pattern. So that's why this doesn't work with every single function. Or it's very difficult with some functions. But you'll see with sine, it's pretty easy. So you just do f of 0, and then you do f prime of 0, f double prime of 0, f triple prime of 0, so on, and you need to discover a pattern in those. So I like to just make 2 columns where I just start doing f and then f of 0. So the 0th derivative is just sine of 0, which is 0. And then I go down where I say f prime is, in this case, cosine, and then f prime of 0 is cosine of 0, which is 1. Right, cosine of 0 is 1. Okay, and then just keep going. Keep going until you dig the pattern, basically. So f double prime is going to be negative sine, which means f double prime of 0 is going to be 0 again. Maybe you kind of get the idea that every other term is going to be 0. How about that? Okay, so it's going to be missing terms. F triple prime is going to be negative cosine, so f triple prime of 0 is going to be negative cosine of 0, which is negative 1. And now notice what's about to happen. The 4th derivative, okay, the derivative of negative cosine is sine, so this is cyclical. Now we're back at the top. So f4 is sine, and so f4 of 0 is 0 again. Let's go one more, just so you believe me. f5 is cosine, which means f5 of 0 is cosine of 0, which is 1. Okay, and now again, we're just back to where we started. So you can see it's going to be 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. Okay, so we're only interested, so now we can start putting it together. Really, only every other term is going to appear in the actual series, right? So that's just my formula for the terms of my Taylor series, or Maclaurin series. I could say Taylor because that's generic. So let's actually write them out, or then try to come up with like summation notation. So I think this is the best way to do it, is to actually write out a bunch of terms of the sum, and then just simplify it if you can, and then say, okay, how do I want a formula too for the nth term. I don't just want to see it like this. I want to see it in series notation, just because, I don't know, it's nice to see. So it's going to be 0 plus 1 over 1 factorial, which is just 1, times x, plus 0 again, minus, okay, so now we're here. So x cubed over 3 factorial plus 0, plus x to the 5th over 5 factorial, right, because that just comes from here. So now you get the idea. The next term is minus x to the 7th over 7 factorial, plus x to the 9th over 9 factorial, right? So it's just the odd powers of x over their corresponding factorial, and also it alternates, right? So this is going to be an alternating series, so we need a little -1 to a power to make it do that. All right, so this is it. This is our polynomial, which, remember, once we graph it, you'll see it looks exactly like a trig function. It models the function sine of x perfectly near the origin. So now we don't need, but we want a formula for the nth term. So think about what we need. We need a -1 to the n, because that'll make these, right? So the 0th term is positive, the first term is negative, the second term is positive, the third term is negative, right? If we start n at 0, this is the 0th term. So we can just have a -1 to the n in there, and that'll make it flip the way we want it to. We also need some odd powers and odd factorials. So the general way to write an odd number is 2n plus 1. Right, so the 0th term is 2 times 0 is x to the 1. The first term is x to the 3, so that's 2 times 1 plus 1. 2 times 2 plus 1. 2 times 3 plus 1, right? It's just, in other words, 1 more than the even numbers. Just 2n would be the evens, 0, 2, 4, 6. 2n plus 1 is the odds. And then the factorial is exactly the same. It's going to be over 2n plus 1 factorial. Right, so there it is. Very famous power series. It is the one for sine of x. So it's -1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. You can drag that out as far as you want. These numbers, these factorials, get really big really fast. In fact, I don't even know what 9 factorial is. It is enormous already. So that means that the further out the terms go, kind of the less they affect the graph, which you'll see. So there's the graph. We could, I would leave this as an exercise because it's cool for you to do. If you were to do the ratio test on that power series, you would see that it actually converges no matter what. So what does that mean graphically? That means if we kept adding terms to this, it would just keep getting better and better and better. It would just keep modeling sine x. It would just kind of expand out. So theoretically, if we had all infinity terms, it would look exactly like sine of x. So it's not like the ones we saw before where they were just like cloistered around a little region. This just keeps going and it works perfectly. Okay, so you can see I think this is just the first 4 terms. So this is just up to x to the 7th over 7 factorial. But you can already see how perfect it is. It goes all the way out to like around 3, it starts to lose it. But as far as near 0, which remember it's centered about that, it looks exactly the same. Right, it looks exactly like sine of x. So one application of this is, we've looked at kind of stuff like this before, but we can use a result to make new results. So we don't have to start from scratch every time we want to build a new Taylor series. So that's just literally what we just got copied, so you don't have to copy that again. But now let's say I want a Taylor series for something like sine of x squared. Could I start from the ground up and start taking derivatives of sine of x squared and doing the process we just did? Yeah, feasibly, but we don't have to, because now we just have, okay, if this is really true, which it is, this trig function equals this infinite degree polynomial with only odd powers. Sine is an odd function, odd powers. Then all we have to do is we can manipulate them if we just manipulate both sides. So sine of x squared, let's do that one. So I should just be able to stick an x squared in here and stick an x squared in here and get it. And I can. And that's exactly what you do. It's that simple. Okay, so we just replace x with x squared. So it's -1 to the n times x squared to the 2n plus 1 over 2n plus 1 factorial. Let's actually multiply these exponents together. So it'd actually be x to the what? 4n plus 2. So if you think about all those powers from it, like the x cubed over 3, whatever, all those powers just double. And there's some terms of it. So it's x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. So it's like 2 times the odd numbers. It's 1 times 2, 3 times 2, 5 times 2, right? Okay, so that's it. I think I probably have a graph. Yep, would you look at that? So obviously the red thing is sine of x squared. The blue thing is the first, I think, 4 terms of this series. Once again, near the origin, you can see they are indistinguishable. And then as we go out a little bit, it starts to lose it. But again, it converges for all x, which means if you kept adding terms, this would just keep getting better and better and better. It would be a polynomial of whatever degree, I guess this is an even function, right, even, that just looks exactly like sine of x squared. It's pretty cool. And it's pretty powerful. There's one for e to the x that I think I leave for you as an exercise as well, because it's very easy, but it's very useful as well. And that one snaps incredibly fast. That one converges for all x, and it converges incredibly quickly, just with a couple terms. Okay, so here's one other kind of mathematical application of that. I want you to find a series representation. Basically, I want you to find the integral of sine squared of x. I'm sorry, sine of x squared. Big difference. So think about if you could compute that directly. But don't think about it too hard, because you can't. You cannot. Okay? It's impossible. And not that it's hard, or not that we just don't have the tools yet in Calc 2, or not that we do and I'm not telling you. It is known that that integral does not exist. So this is called a non-algebraic function. Whatever the integral of sine of x squared is, it can't be written in terms of functions that we have in mathematics. And that's known. That's provable. I don't know how, but it's been proven. Okay, so you cannot integrate this, so stop trying. Literally impossible. There is no function whose derivative is sine of x squared. But, like, there's something that measures the area under the curve, and a computer could certainly do it, right? So there's a number here. And so the only way to find what we would call a closed algebraic expression for it is to use its Taylor series. Because as we saw before, a function can be, we saw a function that was like super hard to integrate, and now we have a function that's literally impossible to integrate. But if we have a series representation for it, that's just integrating a polynomial. So theoretically, whatever the integral is, we could get it to as much accuracy as we wanted by just keep adding terms. And this is how one of the ways computers compute integrals and stuff that are literally non-computable. So we can approximate a function that we don't know about with a series, as long as we have a series to start with. Okay, so you just integrate this. Just integrate this term by term. So if you just, well, it depends on how you look at it. I know some people they're fine with just integrating it in summation notation. So the exponent goes up by 1, so it's 4n plus 3 now, and then we have to put a 4n plus 3 down here as well, okay? Because that's just the power rule. Or you can integrate it from here. So it would be x cubed over 3 plus x to the 7th over 3 factorial times 7 plus x to the 11th over 5 factorial times 11 minus blah, blah, blah. Our numbers are getting a little weird. Okay, so when you integrate a power series, you just pop it inside an integral, the integral of this series dx, so this is just this, and then you just use the power rule. Okay, so the 4n plus 2 went up to a 4n plus 3, and we also had to include a factor of 4n plus 3 in the denominator. And that's it. So there you go. That's the integral of sine of x squared, right? And again, if we stretch it out to infinity, like it really is right. So this is it. This is we just integrated a function that is impossible to integrate. Cool. So if you write out some terms of that, again, the numbers get weird. So it's like 6 times 7, and then 120 times 11, and then 7 factorial is 5040 times 15. So since we don't have a normal function for this, I can't show you the graph and show you the real thing, because there is no real thing. Okay, I could show you the graph of this, but all you could say is, well, I guess that looks like it could be the integral of sine of x squared. So you could, but you'll just have to trust the math. Okay, so we could numerically approximate the value of the integral of sine of x squared for any number now by just using some terms of this power series. Okay, another example of the most famous function with no integral is the one that gives you the bell curve. It's e to the negative x squared. That's probably one of it's probably the most useful function in all of mathematics, is the one that gives you a normal curve or a bell curve in statistics. That has no integral though. So we used a similar method, and I think I'll leave that as an exercise too, because it's exactly the same. Oh, so lastly, I just wanted to do one that wasn't centered about 0, just to so you have an example of that. Like, you can't just do this with any function. And I would encourage you to think about doing it with tangent. If you try to come up with a Taylor series for tangent, you'd start taking derivatives, but think about the derivative of tangent is secant squared. The derivative of that is like 2 secant squared times tangent. The derivative of that gets even more complicated. So every time you take a derivative, it doesn't loop or anything. It just keeps getting more stuff. So you would have a hard time finding the pattern. But for this one, you can. So there's one for cosine that I'm sure I make you do at some point. And there's one for e to the x, and there's one here. And those are really the famous ones. Those are the big ones. Okay, so let's do it. So the process is exactly the same. Just do f, and then f of 1, and then f prime of 1, and then f double prime of 1, f triple prime of 1, and just once you see the pattern, stop. Okay, so ln of 1 is 0. Now, keep in mind why we're doing this. There is no natural log of 0. Natural log is undefined there. So we're just going somewhere where it's defined. There would be no point in doing this about 0. Okay, so now just do f prime. So f prime is 1 over x, and f prime of 1 would just be 1. Okay, so there's no first term. Do it again. F double prime is, okay, this is actually x to the negative 1. So f double prime is negative x to the negative 2, or negative 1 over x squared. And f double prime of 1 is negative 1. Don't stop, because if you just like went from now, you'd be like, oh, it just flips back and forth between 1 and negative 1. No, 2 terms is not enough to determine a pattern. Keep going. So f triple prime, I sort of did some quick math here. This is negative x to the negative 2, which means f triple prime is positive 2x to the negative 3, or 2 over x cubed. And then f triple prime of 1 is just 2. Okay, so you can do a little sidebar to see how I got that, but I just did like the power rule basically in my head. Okay, so like you don't know the pattern, right? Because now it's a 2. So do it again. This is 2x to the negative 3, so the next derivative is going to be negative 6x to the negative 4. And that means the fourth derivative of 1 is going to be negative 6. So now maybe you're kind of seeing a pattern emerging. For one thing, you're seeing the flip. So this is another alternating series. That's cool. And then you have 1, 1, 2, 6. Do we know those numbers? We do. Let's do another one, though. So this is negative 6x to the negative 4, which means the derivative of that is going to be 24 over x to the 5th. And that means the fifth derivative of 1 is going to be 24. So just think about what the next one would be. 5 times 24 is 120, but it would flip back to being negative again. So the next one would be negative 120. Okay, so what are these numbers? Well, it looks like we're just taking every number up to whatever and multiplying it by the next number, which, gee, those are factorials, right? So, but now we have to think of a pattern. So this is 1 factorial. This is also 1 factorial. This is 2 factorial. This is 3 factorial with ignoring the negatives. This is 4 factorial. So it looks like the nth term, there's a negative 1 to the something in there to make them alternate, but the nth term is actually the previous factorial. Okay, so like the nth derivative appears to be n minus 1 factorial with a negative 1 to the something in there as well. Okay, so it's the previous factorial. So we have to be specific. So the first term has to be positive, and the second term has to be negative, and the third term is positive. So it's like the even terms are negative. So if we use a negative 1 to the n minus 1, we'll get it where we need to be, right? Because that way the first term has an even exponent here, so it's positive, and the second term is negative, positive, negative. Okay, so we have to be finicky. And we can't, well, you'll see, we can't really start this series at 0, at n equals 0, but we'll finesse it. Okay, so it's the previous factorial, and then it has a factor of this. So plugging those into the formula for the terms of our, or the coefficients of our Taylor series, they're going to be -1 to the n minus 1 with an n minus 1 factorial. And then remember the n factorial as well. So this came out of the formula for the coefficients of the terms of a Taylor series. That was in there in the first place, right? It was Fn, the nth derivative, which we got, which is that numerator, over n factorial. And now what you should notice if you dig factorials is that this cleans up. Remember, if you take n factorial and divide out n minus 1 factorial, n minus 1 factorial is every number up to n minus 1 multiplied together. N factorial is every number up to that, so that, and then times n. So actually, all those common factors go away. Think about, if that bothers you, think about doing like 5 factorial over 4 factorial. Okay, you'll see what I mean. So the only thing that survives if you divide those things is n. So we get rid of it, actually. And this whole thing just turns into -1 to the n minus 1 over n. How about that? Okay, so that's our nth coefficient. So just remember, with a non-Maclaurin series, there's going to be an x minus 1 to the various powers. So our thing is going to be, well, it's going to be that. It's going to be our coefficients, and then also with a x minus 1 to the n in there. Okay, so if it were about 0, this would just be x to the n, but it's not. So it's x minus, so it's powers of x minus 1, and that's what centers it around 1. Okay, so that's it. That's another famous Taylor series, and it's useful to write out some terms. So notice something, we had to start n at 1 because we can't divide by 0. And that's okay, because that corresponds with the fact that our first term, for whatever reason, actually dropped out. So our 0th term just kind of went away. So if we started on a 0 here, we'd just be like, oh, the first term's undefined. So why not just start it at 1? So that way we don't have that problem. So it's going to be like positive x minus 1 to the 1 over 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4, so on and so forth. Like that. Okay, so that's the power series for natural log of x. Notice, remember how like the natural log corresponded with a harmonic series, because the integral of the derivative of a natural log is like 1 over x. That kind of corresponds with this as well. So we simplify it a little bit, right? But it's x minus 1 to the 1 minus x minus 1 squared over 2, so on and so forth. So there's actually no factorials in this one, which is new, but that's what it looks like. Now, it doesn't work as well as the one for sine and e to the x. I mean, it works. It converges. Oh, I think it converges for all x. But you can see, at least near 1, this is just the first, I don't know, 4 terms. It does obviously match up with the function. Well, because it better, because that's the whole point of this. It doesn't match up as nicely as like our sine did, but whatever, right? Logs are weird. Okay, so that's a couple famous Taylor series. I'd like you to do the one for e to the x, and if you do the one for cosine, you'll notice it's exactly like doing the one for sine. It's just, spoiler, it's an even polynomial instead of an odd polynomial. And there's all kinds of other stuff you can do with it from there. Okay, so those are Taylor series. Thank you.